simple explanation. Let's go on to the next thing. So how do they even work, right? So if you think about a neuron, it has some basic function. It has some basic things in it. It has an input, which is the data that you're inputting. It's usually something that's binary or hexadecimal. It has an activation function, which you're taking the data that you're putting in and then manipulating that data into an output that comes out in a different direction, and then a bias, which then can make the activation function, for lack of a better term, activate more or less. So if you had the bias higher, you want that neuron to then activate more. If you have the bias less, you want that neuron to activate less. And those things are all manipulated based on how you want your neural network to work. All of this goes right back to data analytics and linear regression, which the most important thing to data analytics is to understand that the data is the most important part, not necessarily the thing you're using to analyze the data. If you don't understand the data, you can't do anything. You can't do anything to make the data understood for other people as well. And then this will become more clear as we go on. So always remember that the most important thing, regardless of how good you are at coding or how adept you are at using neural networks or linear regression or anything else, the most important thing is always the data and how understanding the data so that you can manipulate it in the appropriate way. So let's move on. Let's keep going. So that's your basic neuron. These neurons are then put together to create a neural network. A neural network is a bunch of neurons that work together to output once again, a specific prediction or categorization. How do they learn? The weights and biases that were featured on the previous screen are set initially, once again, based on your understanding of the data. It's anybody's best guess. They have best practices, or scientists and data scientists and computer scientists have best practices on how these weights and biases should be set. But nobody knows nobody knows until they really run the neural network and it doesn't work, that they have to start changing them and manipulating them to work in other ways. So the first thing is set the weights and the bias. The bias is how easy the node is to get fired. Calculate the values in the error. So once you run the neural network, it will generate a value. And the value is always the thing you're trying to predict or categorize. When you have a neural network, you run it against test data, and that test data can be any myriad of data that you can find, depending on the data that you're using. That test data has a value that it is supposed to output, depending on what test data you're in, depending on what test data you are inputting into it. And so therefore, it calculates the values, it calculates the error that is generated, and then uses that error to back propagate, which is a long function. It's a really long drawn out way just to say, go back and adjust the weights to make sure that the error is now accounted for. And then you repeat with the new adjusted weights and biases. And so it just does that over and over again. You can almost think of this, you do this in the same way innately in your head, humans do. So imagine throwing a model plane. You pick up your model plane, it's built, it's all nice, it's pretty. You throw it, it goes nowhere. So what do? You say, well, why didn't it go anywhere? Okay, it nosedived. So let me take some weight off the front, add it to the back. That's your back propagation. That's your error accounting. You pick it up, you throw it again. It goes straight up. You're like, okay, well, let me take some weight off the back and add it to the front again. It leans to the side. You take some weight off the side and you keep throwing it until it goes somewhere. And then you also account for your own arm strength. Okay, I threw it too hard that time. Let me adjust. And as humans, we're constantly doing these mathematical adjustments in our head innately that we don't have to like write down or anything. That's how beautiful we are as humans, right? To get things to move in the way we want them to. And so once again, scientists said, how can we get a computer program to do the same thing in the way that humans do it? And they came up with this. So here's the first real world example. And once again, we have to focus on, before we ever focus on how a neural network will work, run, or function, we have to focus on how the data gets it to work, run, or function. The first real world example, I don't know if anybody remembers, this wasn't very long ago. Some of you are probably even rich from it right now. I'm not, or else I wouldn't be here, right? They decided that they would try to predict stock prices with neural networks. Like I said, as recently as January or so, a lot of people made a lot of money off of the fact that GameStop, AMC, and all these other companies, they made a push on Reddit for everybody to start holding all of their, buying stocks and holding them in these companies. And a lot of that ideology that they were going for came from the social media posts that were going on in the Reddit posts. So what they did in response to that is they said, well, if you can do that with that kind of thing and affect it in that kind of way, why don't we just run a neural network to see how much social media generally affects the stock prices? And so they scanned sources such as Twitter. It was mostly Twitter and news articles on stock. They actually picked, this was actually in China, so these were all Chinese stocks, and used semantic analysis to place words in a polarity lexicon. So now hold on. Fancy words, right? All these fancy words, what do they even mean? So a semantic analysis is basically when you take words and you try to figure out what the emotional response is to those words. So if I look at my screen and I say, oh, I hate this screen, what is the emotion that I'm trying to convey by saying I hate this screen? And then semantic analysis specifically written. So if I type on Twitter, I hate my laptop, and I pull that off Twitter, I want to be able to understand what someone is actually trying to convey by saying I hate my laptop. And then a polarity lexicon is just as fancy as saying, is it good or bad? If I say I hate my laptop and I do a semantic analysis on it to see what kind of emotions that is, so is that angry, happy, blah, 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 and I put that in polarity lexicon, that angry, happy then transfers to this is a positive emotion or this is a negative emotion or a neutral emotion. Technically, polarity is usually one or the other, but a polarity lexicon usually includes all three. After it gets one of those three values, it then puts it into a neural network, which is the thing we went over before. And so after much playing with the neural network and doing a lot of research and manipulating the data to find out what the appropriate parameters were and what the appropriate constraints were, they realized that they were actually able to predict stock prices with varying levels of accuracy, but it was only within the span of the same day. So you could take, I think they took about a year's worth of stock prices, and only up to the day in which they were predicting it could they only up to the day in which they ran it could they predict the price of the stock. So here's a couple of the stocks that were running. These may not be so familiar to any of us because we're not in China right now, but that's okay. You know, we can just look at them and enjoy them. A couple of words you might be unfamiliar with is here as well, the lag. And an LSTM, well, I'll go over an LSTM neural network in the next slide, but the lag is an important piece. It tells you how much time should you wait to maintain data before you move on to the next data set. And that'll be important later once again. And then the epoch that's running is the number of times you're going through the full data set before you go through the full data set over again. One thing that's very important to note with neural networks is it's very easy to overtrain or undertrain neural networks. As in, all you're doing, once again, like I said with the model airplane example, I'm throwing it and I'm throwing it and I'm throwing it until I can finally throw it accurately enough that I can get it until I'm finally throwing it to the accuracy that makes me happy. And so what you don't want to do is to keep throwing it and throwing it and throwing it, and then you throw it for the thousandth time. You're great at throwing this model airplane. Someone gives you another one and you can't even throw it anymore because now you've overtrained yourself to throw this specific type. So with epochs, you always want to be able to throw your model airplane in the specifically accurate amount of time so that you're never throwing it too much that you can't throw another model airplane, but then you're also not throwing it too little so that you can't even throw the one you're throwing. So as you can see, they've picked these specific numbers of epochs. 100, 200, 300 are actually pretty good for the data sizes they were going for. It's not too much, it's not too little. You can tell that they had to change them specifically to the lag and the type. I'm sure they probably had, usually when the epoch is higher, you don't have as much data. So they probably had less data sets for this one. And they probably had more data for this stock in particular. And you don't really see any trends with the accuracy with the epoch itself, but you can see 76% or 80% is actually pretty good for a neural network if you're running it about 200, 300 times with probably like tens of thousands of data. I'm sure they could get it better if they had more data, more time, more epochs. You need a lot of memory and processing power to do these things. So it kind of is what it is. And so what did they use to do this thing, right? I mentioned the LSTM neural network. This is long short-term memory. So what long short-term memory is in terms of a neural network is sometimes what you need is the previous data that you ran in order to process the next data. This is also specifically useful when you're doing language processing as well. So if I'm saying a sentence and I say, And this goes back to the semantic analysis. If I say a sentence and I say, hey, I hate pie. And every time I say I hate pie, someone in the chat throws their pie in the trash. I want my neural network to know that I hate and pie is the sequence to know in order for someone in the chat to throw their pie away or to throw their pie in the trash. If I only know I and hate, I'll never be able to get the correlation between me saying I hate pie and you throwing your stuff away. So you have to in some way always memorize the last piece of data. And the way they're processing data isn't in parallel, as in they're taking a whole paragraph and they're putting it all in one and then shipping it off. They're putting maybe one sentence and then the next sentence and the next sentence. So you want to be able to have some memory in your neural network in order to process everything in tandem. And that I have this group of data that's going through and giving me this output and not just this one thing that's going through and giving me this output. Whereas other neural networks is just processing in parallel, the list of inputs you give it, and then not memorizing what the last input was in order to adjust the current input, or at least not in the way that it's memorizing it in a sequence, as in I need to know the sequence of things in order for it to work appropriately. Also, this is important for times when you need the previous day in order to understand what the data is doing. So for example, in this, you can see that the stock price on one day is slightly dependent on the previous day as well, just as much as it is dependent upon what someone is saying on social media. And so you want to have the previous day's price stored, because if you don't have the previous day's price stored, you'll never know the effect that it has on the next day. You'll only know what the current state is. And in this context, it's not stateless. It doesn't need the previous state to run. So I hope that was clear. I really wish this was in person. This is one of those things that I really wish I could hear the questions or like look at faces to understand if people have questions or not, but that's okay. If you, of course, leave questions in the chat if you have any. And I hope I'm doing a decent enough job explaining what's going on here. As you can see, there's a bunch of sticky notes here. These are the memory. This is to represent the memory that's going on the screen, or this is to represent the memory that would go on in this neural network type. So, this row may be one set of data, and then it processes, and then it keeps the set of data to then process this set of data. It keeps this set of data to then process this set of data, until you specify that you don't want any more data processed. And that's where this lag comes in, I want the last 4 sets of data to be memorized in order to process this stock, because this was probably important for them. And of course, in Mandarin, it's not the same character length, it's not the same character type, the sentences are structured the same. So maybe if you were to process them in English, the lag wouldn't be the same type, but it's all up to the person's interpretation of the data. Once again, it's about understanding the data, and then understanding how to process the data is secondary. So let's go on to the next real world example, right? Next real world example is a Tesla, the almighty Elon Musk, right? Sleep while driving. Tesla actually uses neural networks in order to process their self-driving cars, which you could probably guess, but the way they do it is actually very specific and curious, and it's different from the way many other car companies do it. And I want to read the first part because I thought it was very funny when I read it online. It says, Tesla boasts a full build of autopilot neural networks involves 48 networks that take 70,000 GPU hours to train. Fire emoji. Specifically, the fire emoji is on their website. I didn't add that. I didn't just think it was fire. This is they think it's fire. Together, they output 1,000 distinct tensors predictions at each time step. So that's a lot. That's incredible. Like for any neural network, even for something as big as or something that's specifically using deep learning, which is what this is using. That's a lot of stuff to run at one time. And so let's just go on and talk about it, and then we'll go into talk about how they implement this. And then once again, talking about how people are implementing it is important to, if you want to take this back to your work or your school or wherever you're listening to this from, there's not just one way to implement these things, just as much as there's not one way to analyze the data. So you have to, the more you can understand the different ways that people will use neural networks to implement their processes, the more that you can either copy or tweak those things to implement your processes as well. And so Tesla's cars use 8 different cameras to process images and the multiple layers of neural network. That's important because usually cars would use LiDAR technologies. Now, if you're not familiar with what LiDAR is essentially sonar with lasers. So it shoots a bunch of lasers out, usually in like a circular fashion, picks up where the lasers bounce off of, and that's how it measures distance. And then when you're traveling, especially if you're traveling fast with cars, you want the lasers to be able to bounce off quickly because it tells you how far you are from the thing and how fast you're moving towards it. Elon Musk said he didn't want to do that because he's the ethereal Elon Musk. He decided that it would be, because LiDAR technology is so inefficient and old, that it would be better to use the multiple cameras and radar sensing technologies that are on the Tesla to be able to read the 3D space around the car and the velocity in which the car is moving, and then input that to a neural network to be able to process where the car's location is. Now, the build time or the train time of the neural network that's actually run in a Tesla has taken years to become more efficient. You can see even underneath that, it specifically says that there's 50 different neural networks that are used in conjunction in order to get the one Tesla to drive in a straight line. That is ridiculous. And of course, not every neural network is assigned to the same thing. Some are assigned to velocity, some are assigned to proximity, some are assigned to, I don't know, braking, light. They all have different purposes, but they all, once again, and you are working in conjunction to be able to do what a human does without effort. Like when you put your foot on the gas and you put your foot on the brake, you're literally just taking the input from your eyes to process what you should do with your legs. Whereas a neural network doesn't know any of that. It just knows I'm just getting data and I'm going to spit out whatever I'm specifically trained to do based on the test sample I got and the expected data design that I was given. And so that's how that goes. And so it was developed in using PyTorch. They may be switching to C++ at some point. I actually read an article recently. So if you think that one of the other things I want to convey to you in this presentation is that if you think all of this stuff is beyond your understanding, if you know Python, you're literally 80% of the way there. You can develop this in PyTorch if you wanted to. There's nothing stopping you other than yourself. You can sit down today, go figure out what radar they're using. The PyTorch is relatively open source. Get PyTorch, get on Python, and then develop your own self-driving car if you really want to. Now, it's not as easy as that, right? It's a little bit more difficult than sit down and just do it. But if you really had the time and energy and Elon Musk type money, you could do it if you really wanted to. And there's a picture of a guy sleeping. I wish I could sleep in my car right now. I'm so tired when I come in the morning. So how do they get this done, right? I said specifically earlier that they have 70,000 GPU hours of training done, 1,000 distinct predictions at each time step. A time step is usually like a millisecond or a microsecond to a millisecond, 50 different neural networks. How do you get it done? And what they're using is called a HydraNet. Now, a HydraNet
is... before we
continue
on, I think we have a couple relevant questions.
Okay, yeah, I'm listening.
Since you were open to receiving them during the presentation, I thought I'd bring those forth now, if that's okay.
Of course, go ahead.
Okay, great. So the first question is, what are some techniques for understanding the data before designing a neural network?
What are some techniques for understanding the data? So I think that's actually a really good question. The very first thing I could think of is, in order to understand the data, you really have to understand what you're trying to do with the data. And then in most of my data sciences classes that I've taken, before we even try to do any, because technically there's a lot of mathematical things you can do to understand data, and to weed out. You can look at the independence of the data, you can look at the dependence of the data, you can look at the variability, the covariances, all these other things that are mathematical that you could, if you really want to know, you can go to school, go on YouTube and learn it. But the most specific thing you have to do first is understand, what are you trying to do with the data? So when people pick up data, a lot of times what I see in businesses is they say, hey, I have this warehouse of objects, or let's say you're in a distribution center. They say, I have these packages that go out every day, and I want you to do a data analysis on them and tell me what I should do to get them out faster. Okay.
Okay.
What does that even mean? Like you have to, it takes more specific questioning. When you're talking about something such as getting out packages or getting out distributing packages faster from a distribution center, what are you trying to do faster? Are you trying to get your employees to work faster to distribute them? Are you trying to get them through FedEx faster? If you're doing shipments, are you trying to get them through the automation process faster? It's about asking specific questions about what exactly are you trying to analyze. The second thing I think you should do is, and these are probably the main two things when you're analyzing, when you're trying to analyze specifically how the data should be processed, is trying to find patterns and in how things run before you try to put them in the system to find patterns in how things run. So I'm trying to think of a good example. So specifically with the previous example where they were trying to figure out how social media affects, stock prices. They already had a hypothesis down before they even went to go put it in a neural network. They said, we've seen the use case of Reddit affecting the stock price the way it did. We've seen previous research examples where they've also done the same thing. We have semantic analysis that proves that when you say certain things, that affects the way people buy them. You have research that's done on, you have modeling that's been done on advertisements and commercials that affects how people buy things. You've already proven that social media affects people mentally. Why not just see if you can take it to the next tertiary step to say that it affects how people spend their money on stock, if you're specifically talking about stock. And so if I'm to shorten the answer, it's to one, ask very specific questions. Don't ask broad questions, or don't try to solve broad problems. The more specific problem you can solve, the easier it will be to isolate the data. And number two, to find patterns before you try to put it in the system to find patterns. So before the neural network starts failing and you start noticing that things fail, take yourself outside of the process and look at where things seem to trend together. And a lot of that also comes from doing a statistical analysis as well. Like when you analyze covariance, that's just seeing what goes together. When you analyze dependence, that's just seeing what goes together. A lot of those things can be mathematically done, but they can also just be visually done. So yeah, I don't know if that was a very complex answer. I hope that answered their question. I think you said there was another one as well.
Yeah. So this one, the questioner thanks you for your excellent answer.
Okay.
Yeah. So the second question is, I'll leave this to you on whether or not this is something that will be answered through the rest of your presentation. But they would like to know what types of software tools are used to design and run neural networks.
Okay, I'll answer that later. So that'll be answered towards the end. And then if I don't answer it, maybe this person can ask their question again, and I'll try to get an answer for them.
Okay, sounds good. We do have a couple other questions that I will hold until a little bit, later, either during or post presentation. So I'll let you continue. Thank you.
Okay, yeah. So I've got two more real world examples, and then after those two, you can shoot those questions if you want.
Sounds good.
So specifically back to the example with Tesla. So Tesla has this big thing that they're running, right? They've got all these neural networks and it's doing all this crazy stuff, and they're bragging about how they're so much better than LiDAR, right? How are they getting away with it? They're getting away with it with this deep neural network called HydroNet. And what HydroNet does is essentially a bus of branches that hold neural networks individually, and it has a gate, if you can see this gate right here, that then tells, based on what the input is, and this, we could call this a filter, almost like a filter right here, what it should be picking, or what neural network it should be picking in order to process correctly. Because if you're doing velocity, if you're trying, for example, if you're trying to analyze the velocity at which the Tesla is moving, you wouldn't necessarily want, let's see, this neural network is to do position, this neural network is to do velocity, this one's to process, I don't know, torque, whatever. You would want most of the data to go to the velocity branch, but you wouldn't necessarily want the position branch and the torque branch to turn off. You just wouldn't want that data to be processed as heavily. So this gate would then tell these branches, hey, well, okay, well, we talked about bias before, and lessen the bias on these branches so that you're not processing as much data here. And then increase the bias here so that you're really pushing the data here. And then after all that data is processed in these branches, it's combined in this combined section, and then sent to your whatever prediction and error calculator is at the end. And that's a really loose, that is probably the loosest way that I can explain HydroNet without getting into like the deep server switching architecture that's involved in it. But just know that that's loosely how it works. And then there's a really pretty picture of a Hydra over here. You know, these are the branches, and then here's the combined. You know what I'm talking about? Yeah, y'all have seen Hercules. Y'all have seen what is it? Nutty Professor Hercules. That's, you know, that's what that is. Or How Hydra. You know, whatever. Pick your poison of show or movie that you want to watch. But that's how they keep doing that. So very complex process. Shout out to Elon Musk for doing all this, even though it's not him. So like, not shout out to him. Never mind. Billionaires, right? The next real world example is about flight delays. So a bunch of researchers actually saw some gaps in the way that they were analyzing flight delays. There are two organizations that analyze how air traffic should be controlled in such a way to minimize the delay in flight as much as possible. So the first one is the International Civil Aviation Organization, right? ICAO. I like that. ICAO, you move. And so it says they have enabled a program called the Air Traffic Flow Management with the objective of ensuring that traffic volume is compatible with the capacities reduced ground and en route delays. Whew, that was a mouthful. And then the free route airspace, which does the same thing, but I also do CO2 emissions and fuel waste. So they said, you know what? We see these people, they have their own algorithms that they're using. It's not neural networks. It's probably not even programmatic. They probably have some process in which they use or some mathematical computation they use, the same way they use mathematical computations to decide if there's space at a restaurant for you to sit down. They decided it would probably be more efficient to use a neural network. We could probably do it more concisely and accurately. And so once again, for the person who asked, you know, how do you go about accurately deciding the data, the first thing they did was collect the data. They went to the Bureau of Transportation Statistics. That's another thing that you also have to verify, is that your data is good. Is this an accurate place to collect data from in order for me to even decide whether it's good data or not? Some places may give you similar data, but it might not be accurate data, or the data might also be too noisy, which are, you know, those are also things you can analyze mathematically, as well as just kind of thinking about what type of thing you're looking for from this data. All the flights, there's difference between scheduled and arrived. Yeah, so they just analyze the data, and they just got a bunch of the data from the Bureau of Transportation and Statistics, and then analyze it to see if it was appropriate. A new concept that we're bringing up here is called K-fold cross-validation. When you have data, you don't always have test data. Sometimes you just have data. And so what frequently happens, and actually it's more frequent than anything, that you just have data. You don't necessarily have data that you can do tests on that you know is accurate. So what people will normally do is this thing called K-fold cross-validation, where you take the data and I can't show you. Oh, yeah, okay, you're looking at me. So you take the data and you almost fold it like it's a piece of paper. So they did 70% for training, 30% for testing. So they took that 70%, ran it through the neural network for however many epochs. Once again, that's the number of times you run the full training cycle to train the data. And then after the data was trained, they got to the percentage they wanted. They tested that against the latter 30% to see if that training was correct. So then to avoid coupling, or to avoid overtraining for the sake of the data itself, they shuffled the data and then trained it again on the data itself, with probably the 30% being part of that original 70%. And then you keep doing that, and it's called K-fold cross-validation, as in you're taking data that is already the test data and using that to train on itself. Now, that's not always the best, because once again, when you have test data, you want test data to be as accurate as possible and as test worthy as possible. As in, I want to know that this is exactly what I want my outcome to be. But this is just not realistic all the time. So sometimes you have to take what is real life working data and turn it into test data for your own, because you don't have any real good test samples. And so after doing all of that, they were able to achieve an accuracy of 96% while measuring from the 1st to the 31st of December 2018. You see that they have they got 760,000 samples of flight records, and were only able to achieve an accuracy of 96% without looking at international flights. So they don't even know if this data works. Once again, back to the model airplane, they could have overtrained it specifically for US flights, and then it's just no good overseas. But it's just something you have to account for when you're training this data in a neural network, the understanding that, once again, I can train for the data, I can't necessarily train for the situation I'm thinking of. And the way to do that, another point in picking the data, is to pick data that is as diverse as possible. And how much data can I pick that allows me to account for as many mental situations as I can think of? So what did they do? They did a multi-layer perceptron. Now, this is probably most akin to the initial explanation of neural networks that I gave. And that initial explanation was, you have these neurons here that do things, that have input data that it gets. It has a activation function, and activation function is what separates the useless value from the good value, or the value that it's looking for. And then an output layer, which generates whatever output you're looking for, whether that be a prediction or a categorization, and then compares it to the actual value that you're looking for. Is this correct to what it's supposed to be? And then goes on about its merry way. So their implementation was very simple. Something such as this, where the data is, all they really had to do was pick data. It's not really based on any previous values. It doesn't have any sequencing. It's not so massive that they can't process it. They don't need the data. They don't need it processed very quickly, immediately. A multi-layer perceptron is very good for that, because it's very simple, and it's very malleable too. Like it can process a lot of nonlinear data, and a lot of three-dimensional data. So there you go. And there's the data points they picked, in case anybody wants to know about that. And so the last real world example we're going to go over is ouch, it hurts. Of course, you have to use neural networks in the medical sense. It's what is technology if you can't use it for medicine, right? Medicine, the recession-proof, depression-proof profession. So they use these models, just as a basic example. They were using their models to predict cancer. The researchers that were looking into this specifically, they're called CNN models. Not CNN in reference to the liberal media that your African father watches. No, this is the regular, the regular type of neural network, convolutional neural network. A couple of examples of things they did. They used it to predict disease status, and this is actually the one they were predicting the disease status is the one they were able to do the most consistently. You see it has 89%. That's actually very good for predicting disease statuses. Because specifically processing imaging with a neural network is very complex, because images are there's just too many bytes, or there's too many pixels to register. And images, even though pixels can align the same way, and we'll see in the working example I do later, they can mean two completely different things, especially in something like a heart, where a heart doesn't necessarily have a concrete shape. It's not a square, and it's not an oval, or it's not a square and it's not a sphere. It's kind of like a combination of the two things. And so because everybody's heart is different, it's very difficult to align the images together. So it's for something like brain disease or Alzheimer's, where even looking at even looking at the degeneration in the CAT scan is difficult. It's very good to get like 89% on a neural network. And then they could do the same things with cancer in the lungs and the breast. And so, I guess I didn't do the neural network for that, but that one is called a convolutional neural network. I won't go over that one, because that one is actually real complex. And truth be told, I don't even understand it all the way. But that's the one they use. Convolutional, I guess, just for a background, convolutional neural networks are really good for image processing, and that's most likely why they picked it. So creating a neural network from scratch. Okay, I guess that was the breaking point. If anybody wants to ask a question, or if you had any questions before we get towards the end.
Do we have any questions from any of the attendees at this point, other than those that have been submitted thus far? Okay, I think we can go ahead and continue. It looks like we have about another 15 minutes. I think if we could, wrap it up in about 10 minutes and leave a few minutes for, any post questions, I think,
Right.
that
I
may
can do
work.
that. I can definitely do that. So creating a neural network from scratch. So what do you need to create a neural network from scratch? If you know how to write Python, I think I've said this, I think I said this earlier in the presentation as well. If you can write Python, you can make a neural network. A neural network is a bunch of neurons that have math in them that involve differentiables and matrices. And I'll show you in a second. But if you can do that, if you can deal with differentiables, if you can deal with matrices, you can make a neural network just like anybody else can. You don't even need to know any packages or anything. The thing that I use specifically to make my neural network from scratch was the MNIST data set, MNIST. I forget what the acronym actually stands for. I probably should have wrote that here, but that's okay. And it's a data set used for machine learning. Like they literally provided this, a research lab provided this specifically for people to be able to learn how to do machine learning, neural networks, data analytics, all this stuff. And so the neural network that I designed was it's a multi-layer perceptron, the same as this one right here. And it has two hidden layers. So a hidden layer, I guess I didn't go over that, is just the things that are in between the input layer and the output layer. These hidden layers are actually what make it possible for complex, nonlinear. These hidden layers are what make it possible for complex nonlinear data types to be able to be processed in a neural network. If you didn't have these, you would not be able to process nonlinear data. You would just be doing linear regression, which if that doesn't mean anything to you, that's fine. It doesn't really matter. Just take that with a grain of salt, right? It has a sigmoid activation function. If you can imagine like a giant S, or if you imagine an S, that is a sigmoid activation function. And if you're on one side of the X or the Y axis, you're gonna get activated. If you're on the other side, you're not gonna get activated. And then 10 output nodes, because of course, the neural network that I'm trying to build with the MNIST data set, the MNIST data set is a set of pictures of handwritten numbers. So you're scanning those numbers in your neural network to see if you can then figure out what numbers they are based on the data that's being inputted. You have 10 output nodes because there's 10 numbers, 0 through 9. And then a softmax function on the output nodes to figure out whether the value that you outputted is the correct value or not. So a softmax function is specifically usually used for categorization. So in this specific instance of a neural network, you are trying to categorize whether the input that you got is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so that would be the best one to use. And then cross entropy loss is a really basic, easy one to use with the softmax function just because of the differentiation. So let's go out for a second. Let's back out, right? I've got all this code here. I'm going to show you. And this whole time, I have been running a neural network. Now, as you can see, we went over before, this neural network has epochs. And I might even not even saying that right. It sounds like Tupac, right? Like it sounds like I'm naming the next hottest rapper. But these things have epochs, and when each epoch is running, that's the full data set that is processing to show me what the error is. As you can see, every time I finish one, this is the error that it has, and that's usually like the percentage. So I don't know what this is a measure of the cross entropy loss. I don't remember how to calculate it in a percentage, but it's pretty bad here, right? Let's say it's like 50% of them are right until you get, and then once you get to about right here, you see it really jumps down, especially after the first epoch, it jumps down from 3 to 2, then 2 to 2, and then 2 to 1 after only 4 epochs. So you see it gets trained really quickly. That's something you always want to be wary of in a neural network, because if a neural network is getting trained too quickly, depending on what type it is, that could mean that you're overtraining and that you're not going to get the result that you want, or you won't be able to use this on any other thing. So this neural network isn't finished. It has at least 8 more epochs to go. You can see it's actually getting pretty close. You would want it to be at like 0.0 something in terms of the cross entropy loss, because 0.0 something means you're at like 92%. And I only know that because I just know what this is going to end up as. And 92% is pretty good for something that's just running. Here's some code. One thing I forgot is I don't know if I'll be able to do this. I wanted to give you guys what is it called? I wanted to give you guys a GitHub link to be able to add this to, but I did not add it to my slides. So maybe I'll be able to provide that to somebody and they'll be able to send that out in an email wherever these slides go afterwards, so that you guys can see how this is written. And this has the same functionality that I described earlier. It's just all written in code. If you don't get this, this is also very easily Googleable and probably also very more clearly written. I tried to make notes as much as possible, but you know, I understand it. So it's sometimes it's hard to get out of your own understanding. But yeah, so this is a very, if you ever want to make a neural network, go on the MNIST data set, find the neural network or find the data set that is handwritten numbers, and you can create a neural network that takes in the data. It is about 60,000 handwritten numbers, all 250 pixels of data for each number. And you can just process those and see what you get every time. And it'll be very easy. And you don't have to write it from scratch. There are also other things you can use. Let's actually go back to the PowerPoint. Go to the end. So how do you make one? Someone asked, what are you supposed to use to make this, right? I did it from scratch using Python. You don't have to do it from scratch. There's actually very many tools you can use if you don't want to have to go through all of the math that's involved. That's more data analytics than it is coding. So PyTorch, as I mentioned earlier, is what Tesla uses for their Python code, and I think they're moving to C++. You can also do C++ in PyTorch as well. TensorFlow is probably the most popular one. You guys you're probably familiar with that. Scikit neural network is another one that's very popular. These get rid of all of the calculations you have to do and just allow you to set how many neurons you want, what activation function you want, what outputs you want to use. The Jupyter Notebook is a good Python IDE to use for just machine learning algorithms in general. And then NumPy is a good package to use for just general calculations. I don't think I've ever done anything with neural networks or machine learning that did not use NumPy. Free data sets, the MNIST data set, 60,000 handwritten numbers. Perfect data set for you to use if you really want to get into practicing this yourself. Also, IMDb reviews if you want to get into semantic analysis, which is just reading something and analyzing what these words are supposed to be telling you. If someone says, "I hate this movie," what emotion are they trying to convey? And can you predict that emotion? Can you predict? So what some people have tried to do is, based on the titles and description of movies, predict how people are going to feel about it. And then free spoken digit data set is a good one to use if you want to do audible analysis. So if someone's saying something, you want to be able to predict what they're going to say. That's what a lot of people use to train their voice commands. Yeah, their voice commands for their applications. Platforms to work on. Kaggle is great if you want to join competitions, specifically machine learning competitions. People do neural networks on there all the time. It is a great platform for you to be able to speak to other people who are learning as well, even if you don't want to compete. And it houses a lot of the things such as Jupyter Notebook and Collab that allow you to, it's a platform where you can just put all that stuff on there and it'll run it for you. It gives you a lot of the data sets that are there before. And then Playground TensorFlow. It's not Playground.TensorFlow is not a place where you can code, but it is a place where you can play with neurons and see how they run as you are working with them. And then Google Colab is a good place to just house things like Jupyter Notebooks and your TensorFlow code. So that was it. I hope I didn't go over time. I hope I left enough time for a question. That was it. They're here for everybody. Thank you for listening to my presentation. So here is a curly haired chicken. I thought it was cool because I've never seen a curly haired chicken. And I feel like it could use a pick. So thank you, everybody. Is there any question? Is there time for questions?
Thank you so much, Abeku. And our timing is good. So we do have a few minutes to address any questions. And I know that there were some requests for that GitHub link. So I'm going to forward you my email. And if you could send me the GitHub link, I'll get that to all of the appropriate people so that that link gets disseminated to all of the attendees, if that works for you.
Okay, awesome. So I don't know if you see my email right here. Maybe I can't put it right there, but if you could take note of that, I'll email you or you email me or whatever. And I will
Yep.
get that to you. Also, what I will put in the GitHub link is so that you don't have to download them in this data set. I have those in a CSV file on my machine. And so I can just upload all that there. And then if you pull from the repo, you'll just get all of that and you can play with it as you see fit. So I'll be
Sounds
sure to do
good. I'm shooting out an email to you now,
that. Okay, cool.
and then you can reply with all the necessary information.
Awesome.
So with that said, let's deal with some questions, that were pending in the Q&A. It looks like we have one that was pending in the Q&A, and then I'll open it up to folks on the call. Feel free to unmute yourself, raise your hand, or type your question in the chat, depending on what you're most comfortable with. We have a question here. Someone is asking, how would you recommend a student interested in neural networks start?
YouTube. If you nowadays, if you are interested in anything and you have not started on YouTube, I would highly encourage you to start on YouTube. The sad thing is I don't have a recommendation for a person you should watch. But YouTube is the best place to start. If you don't know how to, even before that, if you don't know how to code in Python, learn Python first. Everyone does Python with neural networks. And if they're not doing Python, they're doing R. So, and then usually if they're doing R, they're a scientist. So I would learn Python because you can, if you know Python, you can pretty much do anything with anything machine learning, automation in general. After you learn Python, then you can go on YouTube and look up neural networks and see what you can learn. There's actually a really great book. I'll see if I know. There's a great book called, see if I can find it really quickly. There is a great book called Artificial Intelligence: A Modern Approach. It's a very good, succinct, and mathematical explanation of how neural networks work from a mathematical level, if you want to know that as well. So I would get this book, Artificial Intelligence: A Modern Approach. And there's a whole section on neural networks and even more if you want to learn more about that. So if you are a student, definitely do that. And then also, if you're a student and you're still in school, take a neural networks class, take an artificial intelligence class, and you will learn about neural networks. Artificial intelligence, machine learning, or databases will probably cover that too, because all three of those things are necessary to really use a neural network to its full extent. So if you would like class examples as well, those are the type of classes you should take.
Thank you. And at this time, I'd like to open the meeting up for any other additional questions. Looks like we have about another minute left. So feel free to unmute yourself or enter any of those other questions into the chat. Okay, I'll ask one final question myself, as a general kind of primer. In terms of neural networks and related artificial intelligence, how do you see this evolving over the next 10 years based on what you've seen thus far?
Yeah, okay. With 5G, things are going to change a lot. One of the main reasons why you haven't really seen neural networks or haven't really heard about the implementation of neural networks that you should have, other than like autonomous driving or using it for social media, is because there's nothing that's fast enough to process information to really use it on the fly. And so now that we have 5G and better processing power in terms of servers and terminals and all of that, it might actually be possible to have, for example, a robot that can on the fly use a neural network to be in a hospital being a nurse. Like those type of things weren't really possible before. And so in the next 10 years, you're going to start seeing things like that. Or even like Elon Musk going to space. You're going to start seeing him put a neural network in a spaceship to get to Mars. And so that things like that were just not, they were mentally, people theoretically had the way to mathematically do it, but they just did not have the technology. And that's really what you're going to start seeing happen. And so if you're in school or if you're interested, now is the time to learn. Like, if you really want to get into it, because now is the time where all the innovations are going to start coming. Now this year and probably like next year. Actually, maybe not. This year's over, so maybe like next year and the year after. You're going to start seeing a lot of innovations, especially in the automotive industry, where they're doing a lot of automation to put cars together and stuff. They're going to be using neural networks to understand what the best way to put a car together is, because before they were just doing it on what the best way for a human was. Nobody really knows what the best way for a robot is all the time. So now they can take the data that they have, understand the data by using a data scientist, and then data scientists can create a neural network to fully understand like how they should be running things.
Awesome. Thank you so much, Abeku, and thank you to all of our attendees for attending today's session. I hope it was informative for you. It definitely was for me. And we definitely have more, to share with you throughout the remainder of the BDPA conference. So, please take a look at some of the remaining events and see, what stands out for you, and attend as you see fit. With that said, I hope everyone has a great day, and that brings this session to an end.